Okay, so let's get started. Hello, good morning, everyone. It's great to see everybody here. Cool to see a great C++ conference back in Israel. I'm Roy, and today we're going to do a little bit of a code dive into some work that I did a while ago about a logging framework that we had. And basically, the talk is not really about logging or about a logger framework. It's more about C++, modernizing old code, modernizing legacy. You can consider it sort of like a code kata, if you know what that is. So let's go ahead and get started. This QR code is for the slides. You can see it here as well. Feel free to jump right in because we're going to look at a lot of code. If you have a screen in front of you, you can do it as I talk as well. My name is Roy Barkan. I live in Tel Aviv. I've been doing C++ for quite a long time now. And currently, for the last 13 years almost, I'm working for Istra Research. We're a high-frequency trading company from here in Israel. We're always doing challenging projects in the fields of mathematics, statistics, technology, low latency. If you're interested in any of that here in Israel, come and talk to me later or send me an email. And I've been in Core C++ in that group since COVID. It really helped me through the lockdowns, and I'm very, very grateful for this group. And I really invite everyone to join the monthly meetups as well. Basically, as I mentioned, what we're going to do today is basically a code review together. Okay, we'll look at some code, see how it is, try to have some challenges for ourselves, and see what we can do with that. So again, this is a direct link for the code ball that we'll see for the rest of the hour. Let's click that. Okay, great. So hopefully you can all see the code. Let me know. Would you need it a little larger, a little smaller? Are the colors fine? Okay, let's start with this. And we're going to have a story in 7 chapters. Okay. So chapter 1, just an introduction. Just see how some old code base used to look like. Some of us will see it and it will look familiar. So we're using C++ 98 at this point only, and then we're using the IOStream library. And it's quite typical to have like a global function that wants to get a logger. Sometimes it can be a little more elaborate, but we're working with OStreams. And then a typical way is to use some sort of a define that will get the logger, put in some basic information that the preprocessor knows, and this is how we'll typically use this library and again do it to log things. So in this example, I want to log hello space world, compiling, and we can see that this is the logged string along with the file name and the line number. Cool? Great. So now we want to modernize it. Everybody maybe here knows already that IOStream's library has a bad reputation. It's considered relatively slow in runtime. It's considered very, very hefty. It does a lot of memory allocations. It's has a lot of boilerplate and supports many, many features that we don't want. And for that reason, people in the C++ language wanted to replace it. And the main replacement is the format library. So let's look at the format library a little bit. So in C++ 20, it exists in the format header. And basically, if we have an OStream iterator or any iterator for characters, we can use it very similar to the way that people use Python loggers. So we have the format2 function. Format2 function will accept the first argument, which is an iterator of characters that can push characters into one by one. A format string, which is something that looks very, very familiar to anyone who's logged things in different languages. And then arguments. And the basic idea here is that every curly brace here corresponds to one of the arguments. This is basically done to be very, very safe in terms of compilation time, validations. So if I have a different number of braces than the number of arguments, the compiler will let me know and things won't compile. If I try to put in some type of argument that doesn't, the format library doesn't know how to format, I'll get a compile time error. And if I try to do any fancy annotations to the braces to maybe print the different precision levels to the double here, again, the compiler will tell me if I'm doing anything wrong. The main thing about this is it's a very, very strong library, and it's very, very fast as well. It does a lot of compile time checks, But the main problem with it, or something that people, obviously talk about it a lot, is the fact that this format string is something that needs to be known at compile time. If I don't know the format string at compile time, I only know it at runtime, I need to do something else. I need to use v format. So v format is sort of like a dynamic version or a virtual version. And with the v format, I can take any string, even one that's not known at compile time, and I can use v format too in a very, very similar way. Instead of passing arguments as variadics, I create this make format args, sort of a tuple, pass it into v format too, and everything happens at compile time. If there's an error, everything happens at runtime. If there's any error, it won't be caught, obviously, in compile time, so I need to wrap this whole thing inside try and catch, and potentially will get an exception in terms of a format error. Okay, any questions about that? So just to be clear, if I try to just do format 2 with the good old way that's typically recommended, things won't compile because, again, this format string is not known at compile time, and there's an error about calling some const eval function, which is not allowed. Great, so that's our short introduction to old style logging and new style logging. And here's our challenge. Our challenge is to take a code base that has this old log macro and try to convert the code base to use std format. Okay, and the basic idea is that we have thousands and thousands of log lines all across the code base, and it might be an interesting and equally important challenge to try and do a big search and replace on the code or some clang tidy rule. But for now, that's not what I want. I want to keep the code as it is, but under the hood, instead of incurring the compile time cost, I want the runtime cost. Excuse me. I want to use the format library to catch issues at compile time. I want the better performance. I want to get all the benefits of std format without changing our code base. So ideally, a line that looks like this, using these output operators and passing things in very, very C++98 style, will actually run or be compiled like this, with as a print2 function to some stream, and having this format string created. And obviously, I have a bug here. This needs to be 2024, right? Cool. So this is our challenge for today, and we'll try to do make some progress on it. I'm not. This is not a promise that we'll get all the way there, but through the path and through our journey, we'll hopefully learn some things about modern C++ and about ways that we can adapt various classes, various pieces of code, and basically juggle between runtime and compile time. So chapter 3, first part, is compile time strings. Okay, so here's a static string. This class, you can see, is the template. It's templated on its size, and the basic idea is that it only holds an array of the same number of characters as the size. And this is what's known as a compile time string. You can see it's the basic reason that it's called this way is because of its constructor, which is const eval. Okay, so the constructor is const eval. That means that the only time in which I can construct this type of class is during compile time. And the idea is that although the class is templated on n, and if I have, for example, two objects of the same length, there will be the same type of static string. The compiler will be able to create different objects at compile time and use them as if they are different. And I can use comparison operators to make sure that they seem right. And I can even perform some conversion to a string view again at compile time. The cool thing here is that I don't need to specify the size of the static string when I create it, because I can use deduction guides. People know about deduction guides already from C++17. And in this case, I want to be do something a little tricky. I want to be able to create a static string from the literal string hello and make it become static string of size 5. Okay, the reason that this is tricky is because in C++, this literal actually has a size of 6 because of the trailing null character, the delimiter, and I don't want to hold it inside my class. And that's why this deduction guide has n-1 in here. Okay. So after I've done that, everything is done in compile time. I can use static asserts to make sure that my code works. And we can see here that the size of the static string is exactly 5 characters. We can use comparison operators. Due to C++20, all I needed to do is implement equals. And I also automatically get the not equals operator for free. And again, a static string of hello is not equal to static string of istra because there are two different static strings, although they're exactly the same type. Okay, the type is a static string of size 5, but different objects. And again, once I have those, I can also do manipulations in compile time. So basic manipulation is concatenation. Here I do an operator plus that's also done at compile time between two static strings of two different lengths. If I have a static string of length n1, another one of length n2, I can concatenate them and get a static string of length n1 plus 2. You can see that this is all done in compilation time at const eval, but inside the function, it's not like the result is constant or anything. I can create it, and then as I create it, I can copy information into it. But once I return the result, then that result is hung into place and will not be able to change. Yeah?
Would it handle mixed character types, string and W string, Unicode, etc., or you have to multiply the function?
Yeah, okay, so the question is, will it handle different character types, like wide characters, etc.? So this example does not handle it. The char here is hard-coded. If I would really wanted to, I could add an extra template argument here for the character type. But this is, but yeah, so it's possible, but it's not.
Dealing with multiple types of
yeah, basically, the compiler supports it. You can have static strings of any character type that you like. You can have integral arrays, etc. as well. For our use case, we'll stick to char. Great. So again, I can take a static string of 2 characters, concatenate it with another static string of 3 characters. I get 5 characters back, all nice and good. Compiler checks that everything is great. And if you want to make things even more convenient, then ever since C++11, we have this double quote operator that lets us create user-defined literals. So this user-defined literal STS would just take a literal that's known in compile time and convert it into a static string. So again, instead of writing the whole static string word, I can just shorten it to underscore STS. So now I get underscore STS of HE, and LLO is hello. All, again, very nice. And we already see that we're using a feature from C++20 that's called non-type template parameters, or NTTP. And this is what, let's say, the template, excuse me, the template function be templated on a class that is known at compile time. Okay, so this class has there are various requirements. It's called a structural type, and any class that's the structural type can be used as a template argument instead of using just ints or other objects. So that's NTTP, and this way, this operator quotes is sort of like instantiated separately for the string HE and for the string LLO, etc. There's a different instantiation for every static string that I want to use it with. Even if 2 separate static strings are of the same length, they'll have different instantiations of this function. Yeah. Sure, I can speak a little bit slower, hopefully, and yeah. Okay, so let's do a little bit of more compile time tricks just to get a hang of this. And because everything is known in compile time, these objects, you can see that they're different objects, or HE is an object, LLO is an object, and each of them takes space in RAM. It's a compile time RAM, but it still takes space. And there's a few tricks that you can do to basically convert and move our world from an NTTP world into a type-based only world. So this CTS is like a compile time string that is actually empty in size. This CTS base is only 1 character long, and this class CTS, which derives from it, also is only 1 character long. Okay, its size of is exactly 1, but still it holds this HELLO string inside it, inside the type. Okay, the basic idea here is that if I'm templated as NTTP on some information that's known in compile time, I can take that string and move it into like a static const expr variable. It's a static variable. It's held once for every object that I create. I don't need, or for every type that I create, I don't need to multiply it each and every time that I want to. Again, I can create an equals operator. Notice that the equals operator for these compile time strings basically always returns true. Thank you. Why does it always return true? It always returns true because I'm templated on the actual string that is my data. Okay, I have no data to compare with. So if I have two different CTS objects of different strings, there are different types, and for that reason, I won't even be able to compile this operator equals for two objects of different types. Okay, if I wanted to do that, I'd need to have this operator equals be templated as well on the other type of the string, and on other types of string, I might just return false. Okay, so again, to be clearer, CTS objects, they're templated on the strings that they hold, so they themselves are objects of size 1, just 1 byte, but still I can access their : data, the static member, and see that member is equal to the static string. So if I want to have static strings or strings at compile time, I can have them as non-type parameters, which are basically arrays with information, or I can have them as special types that are instantiated separately for each and every different string that I want. Okay, again, for convenience, I can implement this UDL, this user-defined literal operator, and again, I can see that if I use this underscore CTS suffix, it's just as if I wrote this entire template gobbledygook myself. And again, I can also compare a regular or NTTP type static string with the instantiation type compile time string through the access to the static member.
One operator doesn't radically just use the same type, right? Because it always returns true.
Yes. So again, the question was about equality of CTS, and that's true. Equality doesn't do anything. It just returns true, because if I try to compare one CTS object with another and they are exactly the same string, this will compile, and all I need to do is return true. If they are different, then this operator equal will not even compile, because it's defined to only work with two objects of the exact same type. Yeah?
So actually, if you would use a different string, it won't compile.
Yes, correct. If I use a different string, it won't compile. We can try and give it a go. And you can see that, again, invalid operands to binary expression. Okay, it tries to perform operator equal on two different static strings. One is a static string, is a CTS of a static string of length 5 with these HELLO. The other is of a different length, and for that reason, there is no comparison operator for it. Okay, cool. Okay, the question is, why do I need CPS base? It's a good question. I don't really have to do it to use it right now. I'll use it a little later, but yeah. Okay, so next chapter we talked about strings. Let's talk a little bit about tuples. Okay, tuples are also something that came into our lives with C++11. A lot of includes in order to use them. And let's see what we have. So since C++17 with compile time argument deduction and deduction guides, we can create tuples without specifying their exact template parameters. So a tuple of 1 and C is actually a tuple of int and char. And since C++20, I think, it also has a comparison operator that can be performed at compile time. So I can do a static assert that a tuple of 1 and C is equal to a tuple of 1 and C. Similarly, if I try to compare different tuples, I just get a static assert to be false. Okay? Static assertion is false because 1 and C is not equal to 1 and D. So these are two objects of the exact same type, but with different values. Okay, now let's try to create a tuple element by element. Okay, so I want to create a tuple of my entire log line, for example, and I want to do it element by element as the code progresses. So I'll create this object called a tuple builder. Okay, a tuple builder is templated on a variadic number of types. Okay, variadic templates, again, was given to us at C++11. And the tuple builder basically has this one member that holds its values, and it can accept them as it constructs things and moves them into the values. And it can also just accept a tuple straight up and move it in. Okay, so basically a tuple builder right now is not much more than a holder of tuples. Okay, the reason that I'm using it is because I want to give it some extra operations, and we'll see those operations in a few minutes. So again, tuple builder, very, very similar to tuple. Yeah, okay, so the first constructor here, it accepts a variadic number of arguments and puts each and every one of them inside the member. The second constructor just accepts a tuple as is and moves it inside. Okay, yeah?
Why do you move in line 154 not forward?
Okay, so in line 154, the question is why I use move and not forward. So basically I chose to accept the arguments by value and not by forwarding or universal reference. And that's and the reason is that I want to hold a copy of those types. So if I want to hold a copy, I just tell the compiler, create a copy for me by value, and I'll move it in. Basically, it's also just for making the code clear. I believe if you wanted to try and be as efficient as possible, there might be reasons why you'd want universal references here and forward here, but it's not my focus. And I think it won't give you a lot in this use case, because I actually want another copy of the object to get inside. If a temporary object will get passed in, it won't be copied, because that's the way passing by value works. Okay, cool. Again, just for the sake of ease of use and ease of testing, I implemented the equality operator, which is just doing the default comparison of the values, which allows me to make sure that an empty tuple.
Strategies to improve the ease of use of a test.
Yeah. So an empty tuple builder is equal to an empty tuple builder, etc. Very, very similar to a tuple. And if I try to compare two tuple builders of different types, like one with an int in a char and another with a double in a char, it won't compile. I'm not sure if a regular tuple for stu tuple supports this inequality, but I decided not to do it. I only implemented one equality operator that accepts another tuple builder of the exact same types. Okay, cool. So this is all quite clear and quite fine. And now let's try to use this tuple builder to make some interesting things. And for that, I basically want to implement the output operator less than, also known as chevron, for a tuple builder and an object to build these tuples item by item. Okay, so in order to make things a little easier and to help the compiler help me, I'm first starting with creating a concept here. So we're going to create a context or Boolean, which tells us for each and every type, or if that type is a tuple builder itself. Okay, so each and every set of types is not a tuple builder by default, but a tuple builder of these types is a tuple builder. Okay, so this is basically template specialization for this compile time Boolean or context Boolean. And then once I have that context Boolean, I can use the concept to say that a tuple builder is for any set of types is just anything that looks like whose is tuple builder Boolean is true. Once I have that, I can implement my operator output where the first argument is a tuple builder and the second argument is anything whatsoever. Using concepts here is quite important because, as you might know, there are many output operators in our world. There are output operators that take an O stream and an int, an O stream and a string. There are obviously people that implement classes that look like bit masks or want to do bit operations. They also implement their own chevron or output operators. And I want to make sure that the compiler will not mistakenly think there's an ambiguity, will not mistakenly see two types and the less than operator between them and not be sure which implementations it needs to choose. Okay, so because I only want to take hold of these calls where the left operand is a tuple builder, I use this concept here to make sure that the compiler will not even try to instantiate this function if the left-hand argument is not a tuple builder, okay? And what's the implementation itself? How do I take a tuple builder that already has a tuple and output an extra object into it? I just use tuple cat, okay? Tuple cat, I assume many of you have heard of it already. It's a function that we have in the standard library. We got it in C++11 together with a tuple, which basically does concatenation. It takes one tuple and a second tuple, and it concatenates both of them. Okay, so I have a tuple builder and an object. So I can dig into the values of the builder, create a tuple, wrap a tuple with my object, and concatenate them into one larger tuple containing everything. Okay, again, I'm taking these objects by value to make sure that I own them, and use std move to pass the ownership into this object that I'm going to return. Okay? Yeah?
Why do you use a concept? Because you only have one type. Why don't you just pass the type to the operator?
Okay. So the question is, why do you use a concept, and why is this even templated? And the reason is that there are actually many tuple builders. There's a tuple builder of an int and a string, a tuple builder of an int, etc. So, for example, here, this is a tuple builder with 0 template arguments. This is a tuple builder of an int and a character. Okay?
Can't you just write a tuple builder types dot 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 as the first argument?
Yeah, so potentially I could have made this template maybe variadic, and then put a tuple builder of this variadic pack in here. Then I need to find an elegant way to deal with this last t object, which is different. So this concept, again, it's not a must, but I think it makes code a little clearer. Okay? And once I have this output operator, things start to look a little bit more similar to the way our old logger worked, right? So now I can do a static assert. I create an empty tuple builder, and I use an output operator to add an integer and a character, and what I get in return is a tuple builder that has a tuple of one integer and one character. Okay? And notice that all of this is done at compile time. So inside this operation, there are actually 3 types of tuple builders that get created, right? I create this empty tuple builder, and then I call there's a call to the output operator, and there's creation of another tuple builder that contains only an int, another call to another tuple builder that also adds a char, but it's all done in compile time, so I don't really care about all these temporaries that get created, because eventually these entire things will all fall out and just get this one object that I want. Okay, now let's try and move. We've moved into this inner world of tuple builders where I can nicely use the output operator. I wanted to do it because I didn't want to contaminate the std tuple type. Okay, if I had really wanted, I could have sticked with regular tuples and tried to create an output operator for a tuple and a type. But this basically contaminates the standard library, and everyone else that uses tuples might get confused by that. That's why I moved us from tuples to the tuple builder world. Tuple builder world can create tuples for us, and now I want to extract those tuples back, and I use this tag type called empty endstream to use that. Okay, so endstream is, again, it's just a tag type. It's a type that isn't really used for anything special. I create also just one global variable that's of that type. And I'll implement an output operator that accepts a tuple builder as the first argument and an endstream as the second argument. And instead of attaching an endstream to the end of the tuple, the endstream means nothing. It's just done in order to perform extraction, to extract the values outside of this. So I get a tuple builder of any type as the left-hand argument, an endstream as the right-hand argument, and the return type is actually a regular tuple. Okay, so I use a tuple builder to start creating tuples, and then I use endstream to get the tuple back. Okay, and again, by the way, if people are not familiar of this auto keyword here, that's the way. That's another way that we got in C++20 to create template functions. Okay, so this function is a template function without the word template before it. I just type in the name of a concept, and auto. Even in C++14, we had that for lambdas and this auto keyword, and now we can use it whenever we want a template function. Okay, so again, with this power, I can just create a tuple builder, use the output operators to push information into it, in this case 2 integers, and stream, and what I get as a result is just a regular tuple. Okay, so I have this nice small library that creates tuples for me using this syntax that looks a little bit like logging. Okay, moving on. Let's try logging those tuples. Okay, I have a tuple, I want to log it. So first iteration, quite simple. Let's still use IO streams and not std format. Okay, and we also learn a few tricks on the way. So I have a log function. It accepts, it's templated, accepts something that should be a tuple. Okay, although I didn't constrain it, I planned for it to be a tuple. And I'll get the logger, and then I want to basically use the output operator of this old style logger, the IOStream logger, and output each and every argument. Okay, so let's look at this code a little slowly because it might be unfamiliar to people. The first thing that I do here is I use the std_apply function. Okay, std_apply is basically the way to take a tuple and break it up. Okay, the second argument of std_apply is a tuple. The first argument is a lambda that accepts the specific elements of that tuple as different arguments. Okay, so here I have this lambda that's variadic. If the tuple had 3 elements, then the lambda will basically accept 3 arguments. Okay, if the tuple had 5 elements, the lambda will accept 5 arguments. Okay, and then I want to take each and every argument and print it. Okay, and I also want a space in between. So this first boolean is just a trick to make sure that I put the space right after, right before each and every item, but not before the first one. Okay, so the first one will basically print an empty string, and I use this exchange function that whatever it got as its first argument, it accepts it by reference, and it places false instead of whatever it had. Okay, so the first time it's called, exchange will return true, return whatever the old value had, and places false inside the first. And if I call it several times, then each of the consecutive times, false will be returned. This is a nice trick to make sure that the first time I call it, true will be returned, and each and every other time, false is returned. And this is how I deal with the space in between items, or before each and every item except the first one. And this output operator basically takes an O stream on the left-hand side, and I want to take just one of the arguments. So I write it down as the word args, but actually only one argument is getting passed. And the reason for that is this comma, ... that I have right here in lines 211 and 212. And this basically turns this line into a special kind of expression that we received, I believe, in C++14. Do you know what this type of expression is called? Yes, it's a fold expression. Okay, so once I have an expression with these ... dots, and basically the compiler will stamp out, will create as many duplicates of this expression for each and every argument. Okay, here I basically create all these different duplicates with a comma in between them. So I basically take the logger, log the first argument, comma, second argument, comma, third argument, etc., etc. There are ways to use fold expressions with other operators like the plus operator, etc., etc. We'll also see some examples below. Okay, so we use apply, and we use fold expressions, a little bit of a trickery with exchange. And I have the ability to basically take a tuple of many arguments and call all of call the output operator for each of them. So here's our example. I'll take a tuple builder, put some items in it, convert it back to a tuple, and call the log1 function with that tuple. And I get the result 2, 4, and low, output to standard output. Okay? Cool. Now let's move from IOStream to std format, where we really wanted to be, trying to move a little further into our goal. So this again is very, very simple. Again, I'm using the same apply trick with the same fold expression. But simply instead of calling the output operator for an O stream, I use std format 2 with just one compile time known format string that has two braces. Okay, first argument will handle the delimiter or the space. The second argument will, or the second set of braces will actually deal with the argument itself that I want to format. Okay, and then again I use the first argument, either an empty string or a space. Second argument is the arg itself. So in this way, I've already stopped using IO streams. Now I use the format library. But in some sense, one can say that I'm cheating because if I have a tuple of 5 elements, I'm going to call format2 5 times, once for each element, with a statically known format string, which is the start braces and end braces. Okay, but it works. Happily, it works. Let's again uncomment or comment this line, and hopefully the gods of Godbolt will be good to us. And yes, 2, 4, and low. Great. Moving on. Now let's try to be a little smarter when it comes to compile time strings. Okay, compile time strings are something that are known at compile time, and the basic idea or my basic hope is that I could use these compile time strings in order to call format2 and put those strings as the first argument, the format string argument, and not the second one, so that all the conversion and all the information in them will be known to the compiler as soon as it wants. And the idea here again is to use the static strings that we've looked at before, and this is where CTS base comes from. If someone asked about it earlier, again I wanted to implement a function called format string that can work on any type that is a compile time string. Okay, so any type that's a compile time string, I want this function to be implemented and not on anything else. So a nice trick to do that is to use the derived from concept. Okay, the derived from concept exists. It accepts an argument which is the base class that I want to handle from, and this way any type T that derives from CTS base, and in our case just any compile time string, will have will get an implementation of this FMT string function that basically returns its data. Okay, so FMT string, if I give it a compile time string or template in a compile time string, I get its data, I get this information. And what if I want to get the compile time string or the format string, sorry, of something that's not CTS, that's of an int or a double? What's the format string of a double? And the basic idea is that the format string of a double basically should be open brace, close brace, right? Because any information that's not known at compile time, it's only known at runtime. Its format string has to be open brace, close brace. I need to pass the actual value as an extra argument to format2. Okay? So again, the implementation of this function, it's another overload of FMT string. Okay, another function that's implemented. It just returns start brace, end brace as a static string. But I want to make sure that there's no ambiguity. The compiler knows for each type whether to choose this implementation, the first one, or the second one. And the way to use that, again, has to do with all of these requires clauses that, again, we got in C++20 as a way to make sure that we can write composable libraries and very, very specifically tell the compiler when we want instantiations to happen and when not to. So this is a very, very general template to start with, but I start off by saying, if this type T derives from CTS base, I don't want you to even look at this format string because it might be ambiguous with the previous implementation. Okay. Secondly, I add another validation that makes sure that it's okay to call std format with open brace, close brace for that object. Okay. So if type T, if the STL knows how to format that object, I want this code to compile, and if it doesn't, I want this FMT string function not to even get instantiated, not to compile. Okay, so basically I've implemented two overloads or many overloads, but two types of overloads for fmt string. All of them return static strings. And now I can use the plus operator to create the format string of an entire tuple. Okay? So I get a tuple of many, many types. Some of them are known at compile time, others are not known at compile time. And as I know, but because I know the types themselves, I can create at compile time the format string that I need. Okay, so I take a tuple of many, many items. For each of the items, I'll call this overload. It will either give me the actual string known at compile time or an open brace, close brace. And here again, I use the fold expression, start with an empty static string, and I get a static string for the entire tuple. Okay, so the format string of an empty tuple is just an empty string. The format string of a tuple with two integers and a car is just 3 sets of braces. But if I put anything that's known at compile time, like hello underscore CTS, then this information gets pushed into the compile time string, into the format string that I can pass into format 2 instead of the braces. Okay? So this way, if I have a tuple, some of its elements are known at compile time and others are known at runtime, or some are known as strings, I can basically remove and have the number of braces that I have in my format string will be equal to the number of objects that I actually don't know at compile time and actually need to process in runtime. Everything else will just converse as one single string. Okay, so let's see how it looks like. Again, if I have a tuple builder, again with various items, I can ask for its format string, and I get the exact format string that I want. And this is another step on our journey towards a good logger, right? Because we want our logger to create the format string argument to format 2, and then pass all the extra arguments. So we basically tackle the first item, and we're moving to chapter 6, where we can connect everything. And here I want to start one of our challenges is the case of taking a tuple that has many, many elements. Some are known at compile time and some are not, and filtering only the ones that I need to keep for a runtime. So here's a short utility that can hopefully help us learn, again, a little bit about metaprogramming, a little bit about working with variadics, which is called filter tuple by type, okay? I take a tuple of many, many types and a predicate. Okay, and the predicate basically checks each of the types and tells me, hey, is this type, should this type be kept or not? Do you want to keep it or do you want to throw it away? Okay, if the tuple that I received is empty, I just return it. Otherwise, I'll use the apply trick again to break up the tuple into each and every arguments. Okay, and I'll actually do even one more and take the first argument by name and the rest as another variadic pack. Okay, I'm doing that after I've checked that there is a first argument, the size of is greater than 0. And let's see what I'm going to do with first and the rest, using obviously the predicate. Okay, so I move the predicate into the lambda. I can take like all the rest of the tuple and only deal with the first item. Okay, so I'll take the first item, call the predicate, and check if the return value is false or true. If it's true, I want to keep the element. If it's false, I don't want to keep it. Okay, so I call the predicate on the type of the object first. If it's true, I concatenate the first element itself with whatever will get filtered from the rest of the tuple. Okay, this is like a recursive call. Yeah. Okay, we'll talk a little bit more about type identity in just a minute. And if the predicate returns false, then I can skip this item and just return whatever gets filtered from the rest of the elements. Now, my predicate, I wanted to run at compile time and check the types of of elements and not their values. Okay, and I want also that predicate to be const expr evaluatable, so if const expr won't shout at me. And basically, so I want to just give this predicate one object, like as an exemplar, to just tell me if on that specific object it should return true or false, but I want the return for all of the integers to be either true or false, for all the compile time strings to either be true or false, for everything of every type, regardless of whether the type itself is constructible or not. And I don't want, regardless of whether it's movable or not, copyable or not, etc. So I'm not actually creating the object of type first, and I don't even want to touch the variable f here that I might want to move later. So I'm creating a different type called type identity, which is something we have in the C++ standard, which is just a tag type that lets me sort of again lift my discussion from types into values. So type identity of any type is just an empty type, but it lets me differentiate between different types and use them as different values. Okay, and we'll see an example right here, or a little later. We'll get to an example soon. But this way I can start I have a way that I can take a tuple and break it apart based on some predicate. So now let's see how we can use it by basically trying to categorize which elements in a tuple I want to log by value, log their value, which of them I want to log just by format, and how. So by default, any type, I want to say that it's true, it's loggable. I want to log it. Any type that I see, unless I specialize things later, I want to log it with its value. Okay, I want to just at runtime take the value and log the value itself, and I log it as itself. I'm opening some hook into the future to allow some conversions to happen between the type that is in the tuple and the type that I'm going to pass to std format. Okay. And now let's try to run some specializations on tuple loggable for the non-default things. Okay. So most importantly, if I have a compile time string, again something that derives from CTS base, I also want to log it, but not with a value. I just need to log the string itself. The type is all I need. I don't need the value itself. And lastly, I want to make sure that just regular car pointers, regular just literal string literals car pointers, I don't want them to be logged at all. I want to make sure that if something is just a pointer, and if I decay the type with all these different type trees that allowed me to remove any clutter around the type, if I get a character back, then I don't want to log it. Okay, the basic idea here is that I want to make sure that I can log something that's a compile time string, and I can log something that's a character or an integer, but I don't want to log just a regular string as itself. And the reason that I don't want to log it as itself because I don't want to pay the extra cost of logging it at runtime. Okay, I want to force whoever uses my library to add this underscore CTS suffix to the regular strings. Okay, it's a little bit cumbersome, and if you've seen the lightning talk session yesterday, there was a discussion about how to try and fix it, but it's not easy. But basically, what I'm saying here is that I'm willing to take anything inside my tuple and log it, except plain old strings. Okay, plain old strings. I want the user to be smart about it and tell me, hey, do you want it runtime logged or compile time logged? I can't deduce it myself. And once I have this Boolean tuple loggable information, I can create. I can use use it as a filter. And again, so if I take a tuple of any items, I want to keep only those that need to be stored by value, and I accept any tuple that I want, and I want all the types to be loggable. I don't want this to compile if there's anything that's not loggable. And the result will only be those filtered items based on the predicate that asks, hey, does type T, is it log with value? Okay, so basically every type that's loggable with a value, I'll keep in my tuple. Any type that's logged without a value, like a constant compile time string, I don't need its value. I can just I can filter it out. Okay, so this is my predicate, and again I use for any type T, I take a type identity as the argument, but I basically strip it out, check the Boolean, and that gives me only the filters that I want. And here I basically just created an empty tuple with the exact values that I needed, or with the exact types that I needed. Now I need to fill it, and I use std_apply. Okay, so std_apply here. Yeah, I I go over each and every items of my filtered items. Oh yeah, sorry. And this is where I use the log as mechanism to convert it. If, for example, I want to make sure that a string view or maybe some object that is pointed in memory, I want to hold on to it and freeze it. I want to copy it aside. I can use the log as mechanism to do it. So this basically this loop uses the apply mechanism not to filter information, but to convert each and every object from its original type T to the log as type, which might be a little different. And we haven't seen an example of that yet, but it potentially can happen. Okay, so basically accepted a tuple with many elements. All of them are loggable. Some of them need to log their values, and in other cases you don't need to log their values. And I only keep the ones and the values we need to keep. Let's see some examples just to make sure things are clear. So again, if I start with an empty tuple, then make log tuple just keeps it. If I have just regular values, the regular values, they're all kept. But if I place anything that's known at compile time, I just drop it. I don't need to keep it. Okay? And if I try and put a runtime string here without adding underscore CTS to it, it won't compile. And because there's no matching function to make log tuple, make log tuple again is constrained to not allow these something that's not loggable. If I added underscore CTS here, things will not work because I have the make log tuple will create a tuple of length 3 of length 2, and I'm trying to compare it with a tuple of length 3, which is not possible. Okay, but if I wanted to, I can use the SV suffix. Does anyone know SV? SV is the string view suffix. I think I have it. I'm using that namespace, and suddenly things are working, right? Because the tuple here is again a tuple of an int, and string view, and there's a way to compare a tuple of int and string view with a tuple of int, and the car pointer, and the result is false. So static assert passes. Okay. I have just a few more minutes. So once we have all this information, I can have a function that uses apply, takes a tuple, and only calls the format2 function just once. Okay? So again, I'm using the apply mechanism, but without a fold expression. Okay? I'm using the apply mechanism to break down my tuple that I get as input into a lambda. But what I'm going to do is the lambda will only take the items that are needed at runtime. The format is the full format that's generated as before, some compile time information and some braces. And here I create a single call to format2 that takes this information, converts it to a string view. This is known at compile time, so format2 agrees to compile it. And I'm moving all the extra arguments, the ones that are exactly as the number of braces that we have in the format string. Okay, so here's our example. I don't have much time, but the compiler will hopefully be nice to me. And we can see that again, I'm trying to log with a single format operation, a builder or a tuple that has an integer, a compile time string, and another integer, and it will hopefully work. That's great. Now, the last chapter that we have is trying to move back to the macros and wrap it all together. And again, the basic idea here is that I had this macro called log that takes a logger and also appends a few more details into it, like the file and the line, okay, which are known at compile time. And I want to go and log it. And the way that it worked before is that this generated an IO stream. Now I want to generate a tuple builder, right? So that so whenever people call a log, a tuple builder will be created, and these extra arguments will be added to it. So we can do that. And one issue that's important to note here is that even if the log object tries to start with a tuple builder here, the return value of tuple builder output another tuple builder is a new builder. But I'm blanking out. But I have a small problem. That my first logger, the first piece of information that I want is those file and line numbers, which have to be calculated in a different order in terms of associativity. Let me give a short example of that to understand what I'm saying. So the thing is that I have my OStream iterator that knows how to push things into standard output, and I have a tuple builder, and I want whenever I try to push a tuple builder into the OStream iterator to call this long single format function that I used before. Now that function will work, and will work greatly. But I want to make sure that as I create a tuple builder, this line will first take the second piece of this expression here, concatenate it with the first static string, then with the second static string, etc., etc. And only once the tuple builder is fully built, then I want to call log single line just once. Okay, so if I have an expression like log output hello, output space, etc., etc., I want to make sure that this function is called only once. Although its first argument, the output iterator, is hidden inside this macro, and it's at the leftmost side of the expression. It's a little bit complicated, and if I want the operation on the left-hand side to happen last, I need to deal with operator precedence and operator associativity. And the output operators has one type of associativity, but output assignment has a different type of associativity. So this macro will take a stream logger, but it will combine it with a tuple builder only once everything is done. Okay, so I take a tuple builder, I can concatenate it to the file, concatenate it to the line number, concatenate it to an extra information, concatenate it to some more information, and only once that's done, operator less than equals will be called, which will take the entire tuple, call format just once, and be done. I hope this is clear. I'm happy to take questions. Thank you very much. Let's go to our short summary, where basically my talk here was meant to basically show you that C++ has evolved a lot, like since 2011 until today. There are many tricks and ways to create libraries, to create pieces of code in very intricate matters. But it's just, sometimes we can use it for benefit, even for simple tasks. All day we're looking at large legacy code bases, and we see things, and they don't look modern to us. If we want to modernize things, we can do it. It's all in our powers, and there are ways for the language to do it. And as we play around, the idea is not just to actually complete the task at hand the best way, but also learn a little bit about the language, learn about the possibilities and the power, to find ways where something that might not help us in one project can help us later on, and that way we can sharpen our skills, get more tuned to the language features. So again, thank you very much. I'm happy to take questions. Yeah.
Endstream, where did we lose the object? Where is it? Because it's not in the final example.
Oh, okay. Yeah. So the question is, where do we lose the end line here, the end stream? That's a good question. And basically, if I could have used it, but once I realized that whatever way I turn it, I have to make sure that the last operation in the creation of this entire log chain is the call to format. I had to make sure that that the associativity will take me for such that the last operation done is done with the leftmost argument, not the rightmost argument. And that way, I could cheat a little bit and have this operator less than equal take a tuple builder as a second argument. And because I took a tuple builder as a second argument, I didn't need this end string thing. And that meant that I didn't need to contaminate the log macro. Okay, if I wanted to pass a tuple in here, then I definitely would have needed someone to put some end stream here, which is not the way people usually write to their code base, but it could have been done. Okay? Any more questions? Yeah.
Isn't that log implementation if adopted by a fairly large code base, say, isn't that has the potential of greatly inflating the binary size? Because you're using any permutation of any type, and then any permutation of any string size, and this is
Yeah, okay, so the question is about is this feasible for a large code base in terms of the binary size, in terms of creating these objects for each and every line in our code base where we log anything, creating different types of objects, different types of things. So my basic answer to you is yes, you are correct. This is a a thought exercise and a way of thinking of how we can use the different mechanisms in the language than something that I would go ahead and implement inside a large code base myself. But I want to stress that this is all done in compile time. All the functions that I wrote here as const expr, like a large bunch of them can be even implemented as const eval. They won't really impact the binary size, but compilation times will be horrible. I think the best way to deal with this specific problem or this specific type of project is using something like a clang tidy and actually do a big search and replace across the code base and move everyone to just stop using the output operators, but that's a different story. Hope this answers your question. Anything else? Thank you very much. I apologize for being a little over time.